Okay, so last time we started this algorithm that is going to factor univariate polynomials over rationals. So basically in the input what you are given is f with coefficients ai's which are integers, you can assume them to be integers, and say these integers are given in binary L bits. Okay, so you are given n plus 1 integers, each is L bits. So we are assuming here that these integers are signed integers and their value is smaller than 2 raised to L minus 1. In the output, of course, we want to check whether the polynomial f is an irreducible polynomial. If not, then you have to output an integral factor, non-trivial factor. So the degree should be between 1 and n minus 1 of this non-trivial factor. Okay, so we already actually wrote this algorithm which is called L cube algorithm. So in step 1, it's a basic pre-processing step. The idea is that you pick a prime p and then you factorize f modulo p. What we want, the condition we want on the prime p is that it should not divide the leading coefficient an. So an should be non-zero mod p and f mod p should be square free. In the second step, this is simply a factorization step, so you factorize f mod p. P will be a small prime, so it is enough actually to use Berle-Camp algorithm. Okay, so this will be a deterministic way to factorize f mod p. So let's say the factors are G0, H0. G0 is assumed to be monic, irreducible and co-prime to H0. It's a co-prime factorization. Next is Hensel lifting. Okay, so now you lift G0 to Gk. Okay, G0 is this monic irreducible co-prime factor. So at this point you can apply Hensel lifting lemma constructively and you can lift this factorization mod p raised to 2 raised to k. So it apply k times. K is sufficiently large, so we will see why this parameter is important, but it will be around log of NL, n cube L. Okay. Fourth step will be the step where we will go from Gk to a polynomial G tilde which is closer to a factor, actual factor. So remember that Gk is a factor of f only mod p raised to 2 raised to k, right. From here we have to go to an actual factor, integral factor of f. So this is reminiscent of what we did in multivariate factorization before, right. When we reduced bivariate factorization to univariate factorization, we did a similar linear system step. So here we want to find G tilde and Lk such that G tilde is a multiple of Gk by Lk. Obviously degree of G tilde should be between 1 and n minus 1. Moreover, the coefficients of G tilde should not be too large. So the coefficients of G tilde should have bit size around the same as before, which was L. So now we want it to be around Ln, L times n. Okay, this much leeway we give, but not bigger. And finally, like we did in bivariate factorization, you take the GCD of f and G tilde and output it. Okay, so this is reminiscent of bivariate factoring. We had also started analyzing the steps. So in step 1, what is the prime that will work, right? So we want to look at the case when f given input polynomial f is square full. So suppose it is square full, then what you can do is you can compute the GCD. Just compute the integral GCD of f and f prime, and that will for sure factor f, right. So this is an easy case. Now it may happen that f is square free, but mod p it is square full. So if it is square full mod p, then the GCD of f and f prime mod p will be non-trivial, which implies that the resultant of f and f prime, which is now a number, right, when you take resultant with respect to x, so this is x, when you eliminate x, you are left with an integer, and that integer will be divisible by p, it's 0 mod p. So that's R. So what you want is you want a prime p such that p should not divide the resultant R, and p should not divide an, the leading coefficient. Okay, so we want a prime number p that doesn't divide an times R. Note that an times R is non-zero to begin with. An is obviously non-zero because the degree was n of f. R is non-zero because f is assumed to be square free. So the resultant will be non-zero integer. So just pick a prime which doesn't divide it. Okay, so an times R is by the definition of resultant, it is as big as this, and you can see that this bounds the number of primes by log of this bound. So definitely a prime around L times n will exist and can be found. Okay, so you work with that prime. That is the analysis of step 1. Okay, now let us move forward to step 2. Okay, so what happens in step 2? So in step 2, you are just factoring f mod p. So since p is equal to O tilde ln, it is around L times n in magnitude, factoring f mod p by Berlekamp, factoring f mod p to find G0 is doable in polynomial in prime p and the degree of f, right, which is overall polynomial in NL. So in this much time, which is truly polynomial time in the input size, you are able to find G0 by Berlekamp algorithm, right. So recall Berlekamp for this. So that completes step 2. Step 3 is Hensel lifting. So let's analyze that. Again, recall the k times Hensel lifting. So that we have seen is a polynomial, deterministic polynomial time algorithm. It is polynomial in k and the degrees and the bit sizes, right. So this is by Hensel lifting lemma. This is doable again in polynomial in NL time, right, because k is also picked to be quite small. So everything can be done in polynomial in NL time. Let's move to step 4. So in step 4 is this linear system solving, but there is a catch now. So indeed, in terms of the unknowns of G tilde and Lk, this is a linear system, but not any solution of the linear system will work. So you want a solution which is small in bit size, right. So you cannot just invoke a linear system solver. So this is actually the hard part. This is what will lead us to something new. So this requires a small root of a linear system. So we will see in the next lectures, we will see how to find a small root of a given linear system. But let us first see why a small root will exist, right? It may not exist. So let us first see the existence proof, then we will move on to the constructivity. So let us first estimate the bit size of the factors of f. So we will prove the following lemma. This is called Minut's bound. Any root alpha, any complex root alpha of a polynomial fx. So ai x to the ai are the coefficients and there are n plus 1 of them, degree is n, right, and these are all integers. So any root, so you know that over complex polynomial f will completely split into complex roots. The question that Minut's bound answers is how big is the magnitude of each of these roots. So it says that the magnitude is at most n times the max coefficient. Okay, so ultimately the statement is very natural. It is saying that that any complex root you pick of a polynomial, the magnitude is bounded by the magnitude of the coefficients times n, which is the degree. And the proof is equally simple. So what you basically divide into two cases. So if if you are looking at a root alpha whose magnitude is less than 1, right? Then of course, so in that case what do you do? Well, in this case the bound n times max bit size, that is at least 1, right? So this is trivially true, then the bound holds trivially. Otherwise, the norm of alpha is greater than or equal to 1. So in that case, let us look at the evaluation of f at alpha. Since alpha is a root, obviously it is 0, but on the other hand, you also know that sigma ai alpha to the I is at least so since the norm of alpha is at least 1, this sum, the bigger chunk of this sum comes from alpha to the n. Okay, so let us isolate that a n alpha to the n minus the rest. Okay, so this is the lower bound on this sum sigma ai alpha to the I. We have isolated the highest term and from the rest, looking at the difference of that, which is greater than equal to alpha to the n, because a n will be at least 1, right? It is an integer, so the magnitude is at least 1, it is not 0. So alpha to the n minus ai alpha I is at most, so actually we can remove the sum, use the max instead. This is at most n times max magnitude over all the i's times alpha to the n minus 1, right. So here we are doing two things. One is that the norm of ai will be at most max over all the ai's, and alpha to the I will be, norm of that will be at most alpha to the n minus 1. This is because alpha's norm is at least 1, right. So this and then there is a minus sign, so the inequality is correct. And remember, 0 is greater than or equal to this, right. So which means that what you get is alpha is less than or equal to n times max of ai. Right, which is what you wanted to show. So this is so it's a simple proof. Just look at the evaluation of f at alpha and you will get this. Okay. So this means that the roots are small. Now from this you can talk about the factors. Factors will be small too. So that is lemma 2. Any factor g of f has coefficients of magnitude at most 2 raised to L plus log n minus 1 times n. Okay, so what this is saying is that what did you get in Minot's bound? So you got that the bit size, the magnitude of a root, complex root, is around the bit size of the coefficients, right. So it's kind of n times L. It's kind of n times 2 raised to L. For the factor you are getting something slightly larger. Okay, this is 2 raised to L and then another power of n. It's 2 raised to L times n. Okay, it's slightly more, but remember that this is the magnitude. So the bit size is only ln, right. So in terms of the input size, the bit size is pretty small. So factors cannot be too large. That is the bottom line of this statement. Okay, so the way you will show it is by looking at the complex roots of the factors and applying lemma 1. So, factorize Gx into roots. Let us say there are m roots, degree is m. Alpha is the complex numbers, but Gx is an integral factor. So, these complex roots, they multiply together and then you get integers, and for these integers we will have a bit size upper bound. So, consider this Gx, look at the coefficient of x to the m minus j in G is what? So, this is like picking j of these alphas and summing up. So, basically pick j of these, a subset S of size j out of 1 to m, and then multiply these alphas. Okay, so this is the coefficient of x to the m minus j, and using lemma 1 you can bound this. With magnitude less than equal to sum over all these subsets, then product norm of alpha I. Right, this is by lemma 1, which is smaller than number of subsets is m choose j times, look at a product now, product alpha I. So, lemma 1 says that, so product alpha I, you invoke lemma 1 and you will get n times 2 raised to L minus 1 raised to j, right. So, this is true for every j, and overall each of these things they will be smaller than this. J goes from 0 to m. So, that is the upper bound, right. This is by the binomial expansion. So, m choose j times n 2 raised to L minus 1 raised to j is at most this expression, which itself is smaller than 2 raised to L plus log n minus 1 and raised to m, m is at most n minus 1. So, we can safely put n here. Okay. So, that is the bound for the coefficients of arbitrary factors of a polynomial. Okay. So, ultimately what we have is, once you bound the bit sizes of the coefficients and the degree, so the input polynomial, once you know its bit representation size, its bit size, you also know an upper bound on the bit size of the factors. Okay, you have a decent upper bound on that as well. Okay. So that finishes the analysis for step 4, right. So, step 4, we know that if there is a factor of f, integral factor of f, it will have bit size smaller than n times L plus log n, right. This is what we have shown, and step 4 is trying to find that. Okay. So, if f has a factor, then gk will lead you to that factor, g tilde. So, existence is now clear. How do you construct this? That is not clear. Okay, let us now move to step 5. Why is step 5? What is step 5 doing? So let's go there. So this step also needs a detailed analysis. It's a very important step, but you have seen this before in bivariate factorization. So the analysis will be very similar actually, it will be resultant based. So if G tilde exists in the previous step, and let us say for the sake of contradiction that it does not factorize F. Okay, so step 4 found a G tilde with the appropriately small coefficients, but in step 5 the GCD of f and G tilde is 1. So what we want is actually a contradiction. So let us see how the contradiction will appear. So they being co-prime means that there exists by Euclidean GCD algorithm, extended Euclid GCD, there exist U and V such that UF plus VG tilde is equal to, so notice that I am asking for UV to be integral polynomials, right. So if they were rational polynomials, then UF plus VG tilde would have been 1, but since they are integral, it will be the resultant. Which is non-zero. Okay, so since f and G tilde you are assuming to be co-prime, the Bezout identity will look like this: UF plus VG tilde equal to this number. Resultant now is a number and it's non-zero. Okay, what do you do here? So as you can guess, you have information about how F factors and how G tilde factors. So use that information. So you will get U times F is GK HK and G tilde is GK LK, which is obviously resultant modulo P raised to 2 raised to K. Okay, so modulo prime power, you know how F and G tilde factor, and this gives you this nice congruence where GK is outside. So you get this. Okay, so RHS I have not changed, LHS we see that GK divides. Now this is absurd because on the RHS you have a number and on the LHS you have a polynomial which is not a number, right, it's non-constant because GK is non-constant. So the only way this can happen is if both LHS and RHS are 0, right. So can RHS be 0? Can this number be 0 mod prime power? That's the question. So let's analyze that. When is it 0? What does it mean? So note that the resultant what is the magnitude of this resultant number? So degree of f is n, degree of G tilde is n minus 1. So number of coefficients are n plus 1 and n, so it's 2n plus 1 dimensional matrix when you want to compute the resultant. And how big are the entries? So for f the entries are smaller than 2 raised to L minus 1. For G tilde, the entries are by construction, it's L plus log n times n and then the whole thing n, right. That is what upper bounds the resultant number, which you can see is smaller than 2 raised to how much do you get? So this comes out to be around n square times L, right, and we have picked 2 raised to k sufficiently large. So let me say this is smaller than 2 raised to 2n cube L, which is smaller than 2 raised p raised to 2 raised to k. Right, this is why we pick 2 raised to k to be large enough or k to be large enough. So this prime power is actually much larger than the resultant. So there is no scope of non-zero resultant becoming 0, right. So in equation 1, RHS is non-zero. So this implies that RHS in equation 1 is a non-zero constant, in fact. While LHS in equation 1 is a non-constant polynomial or is a multiple of GK. GKX. Okay, so RHS is a non-zero constant, LHS is a multiple of a polynomial GKX. Now multiples of polynomials are again non-constant polynomials except the 0 multiple, but it's not a 0 multiple. It cannot be the 0 multiple because RHS is non-zero. So that is the contradiction between LHS and RHS. Okay, so that gives you the contradiction, and this contradiction means that the contradiction implies that step 5 factors F if G tilde exists. Okay, so whenever step 4 succeeds, step 5 also succeeds. Okay, so this is an amazing property. So all we have to do is work out step 4. Once we have worked out step 4, step 5 will automatically succeed and factorize. Okay, so we have covered all the steps except obviously step 4 details we have to now work out. Okay, so step 1, step 2, step 3, 4 and 5 is what we have completed. So now let us focus on this missing part, which is step 4. The algorithm hidden in step 4, right? How do you actually compute step 4? with small coefficients. That is the thing. So there is a linear system. We can find a root of the linear system, but then how do you find a small root? That is the new thing you have to do. So let us set up some notation to understand this. So let Gk be of degree n prime, obviously between 1 and n minus 1. Now the unknown polynomials are G tilde, which is, let's say, Ci x to the I, and Lk. Let's give it the coefficients alpha I. And G tilde is Gk times Lk, right? So G tilde has degree n minus 1 at most. So Lk will have degree n minus 1 minus n prime. Fine. So you have to find these with the constraint, satisfying the constraint G tilde is congruent to Gk times Lk mod p raised to 2 raised to k, and the unknown coefficients are Ci alpha I, and in this equation it's G tilde Lk, right. So Gk is completely known. You want to find the coefficients of G tilde Lk. But then the coefficient of, there is a condition on the Ci's that it should be small. Okay, let us do some more jugglery. So let us rewrite it as sigma Ci x to the I Lk is alpha I x to the I Gk, that's the RHS I am writing. Right, so this is what it is, but I want to remove the modulus. For some reason I want to make it exact. So then I have to introduce multiples of prime power. So let's do that. So p raised to 2 raised to k x raised to I. Okay, so let's call this equation 2. Okay, so here the unknowns are Ci, alpha I, and beta I, and it is clearly they clearly are roots of a linear system, and there are also integers. That is what we are looking for. So find integral C bar, alpha bar, beta bars in equation 2 such that C is small, the vector C is small. So, the norm of the vector C is Ci square root, right, that is the Euclidean norm. So, I want this to be small. How small? Well, so step 4 said it should be smaller than 2 raised to L plus log n times n. In step 4, what did we have? The coefficients have bit size 2 raised to n times L plus log n. Okay. So now I am replacing it by a slightly better condition because I know that such a C bar exists, right? By the previous, if you look at the previous proof in this step 5 existence proof, sorry, not step 5, step 4. In this step 4, if you look at lemma 2, the integral factors coefficients were bit size L plus log n minus 1 times n, right. So, each of the Ci is this much, and if you look at the norm of the C bar vector, it is definitely smaller than 2 raised to L plus log n times n. So, this blue bound. Okay, so that is the question. So, we have reformulated the question. You are given these, you are given a linear system with the unknown variables C bar, alpha bar, beta bar, and you want an integral solution such that the norm of C bar is smaller than this 2 raised to L plus log n times n. So, let us now jump into this linear system small root finding question directly and forget about the application that we saw before. Okay, let us just look at this question, and we will invest this class and the next class to answer this fundamental question. We will use something that is conceptually new. You probably have not seen those things. So, the fundamental problem is you are given vectors with you are given m vectors, let us say the ambient space is n. So, you are given m vectors, each vector has n coordinates, the coordinates are all integral. Okay, this is what you are given. Now, okay, let me set up the correspondence. So, B1 to Bm will basically correspond in this equation 2, it will correspond to the basis vectors of the solution set. Okay, so this equation 2 is a linear system, so you can solve it and you can find a basis of the roots. Those basis vectors I am now calling them B1 to Bm. Okay, so that you can compute, you have it. But that is not what the answer that you want. So, you actually want their combination, you want their integral combination such that the norm is small. Okay, so the fundamental problem to solve is that given m vectors in the n ambient space, can you find a small vector that is spanned by them using integral coefficients? Okay, so this gamma 1 to gamma m being integers is important. Okay, so basically to get from this equation to that fundamental problem, you find a basis, integral basis of this, and then just ask the question for that basis. The sigma gamma I bi that you will find, whose norm is small, will correspond to C bar. Okay, so you are interested in finding that C bar. So these z, so we call sigma gamma I bi, we call this a z linear combination, integral linear combination, and the set of these combinations is called a lattice. So the z linear combinations of bi define a lattice. Okay, so just like Q linear combinations, rational linear combinations will define a vector space, Z linear combinations define a lattice. And we will use the following notation. So this L B1 to Bm is the lattice spanned by these vectors. Such that gamma i's are integral. Okay, so for example, how does a lattice look like pictorially? Right, so a vector space, you know, for example, one dimensional vector space will just be the real line, right, and two-dimensional vector space will be the real plane. So in the same spirit, what is the picture for one-dimensional, two-dimensional lattices? So if you consider 1 0 and 0 1, these elementary vectors, right, the x and y kind of axis. So this will be this is 1 2 3 4. Okay, so this is the, let's say, x1 axis, x2 axis, the origin. So where will the lattice points be? So of course 1 0 is a point, and 0 1 is a point, and in their integral combination origin is also there, so that is also a point. But then you can double 1 0, right, so this is a point, you can triple it, you can make it 4 times, and similarly here in the x2. Now what are the other lattice points other than the axis? Well, so this is also a lattice point, right, 1 comma 1, because you can sum up, and by summing up other things you will get these other points. right. So that's it. So this these green points, these are exactly the lattice points, and they are in all the quadrants. Okay, so because you can also you can not only add, you can also subtract. All integer combinations are allowed, so it is on all the sides. So you can also go here. Right, so this is how a lattice looks like. As you can see as you can deduce from the picture, it's a very discrete object. So you really have to jump from one point to the next. There is a big gap between them, and this is happening because you are taking integral combinations and not real combinations. Okay, these are very useful objects, as you will find out in the next lectures. Okay, what is the lattice spanned by 1 0 and 1 1? What do you think? Will it be different? It won't be different because 1 1 is just 1 0 plus 0 1, right. So you can again add and subtract, and you will get the previous lattice. Okay. On the other hand, if you look at 2 0 0 1, what do you think about this lattice? Do you think this is the same as before? No, it is not the same as before, because you have actually doubled one basis vector, and that makes this lattice coarser. Okay, so in the set notation, this is a sub lattice. Okay, so if you scale up a basis, then you will get actually a lattice which is coarser. Okay, there is, for example, there is no way to get 1 0 in this, right. 1 0 is absent. It doesn't contain 1 0. So that but everything that this contains, the previous lattice also contains. So what you will get is actually a coarser lattice like this. On the x2 side, you will get everything. Okay, so what is the question in this lattice that we are interested in? So the question is, given a lattice, find a vector in the lattice which is small. Right? So for example, you can ask the idealized question, find the smallest vector in the given lattice. So if you look at this green lattice, the smallest vector here is 1 0 or 0 1, right. Its multiples cannot be the smallest, but 1 0 0 1 or minus of that, those have length 1, and anything else will have length more than 1. Right. So here pictorially it was easy to see, but as m or n increase, then it becomes a challenging question. Okay, so you basically have to find the right integral combination so that the length is minimized. So that is called the shortest vector problem. So shortest vector problem is SVP. Find a vector V in the lattice such that the norm of V is minimized. So let me write this properly, such that the norm of V is equal to the minimum over all the norms. So over all the vectors available in the lattice, the smallest norm, obviously excluding 0. 0 is always there. So the positive norm, smallest positive norm. That is the SVP question. This is actually, it may not be immediate, but this is a very hard question. And not very long ago, Aitai was the first one to show that this is NP-hard. And soon after, Michianchio showed that constant approximability of SVP constant, basically in particular he showed that if you want a vector that is at most square root 2 times the shortest vector, so an approximately shortest vector, that is also NP-hard. Okay, so this settles the inapproximability of SVP. Not only is it NP-hard to compute exactly, even you cannot even approximate it. Right, so then it would seem that this step 4, where we want to find a short vector satisfying a linear system, that question may be NP-hard. We may have reduced to a hard question. Well, fortunately that is not the case, because we need merely a 2 raised to n approximation. For step 4. Why is that? Well, you look at the ambient space. So that ambient space was, in our case, it was, how many C bars are there? Right, that is only n. And for that ambient space of n, the step 4 requires a C bar to be around 2 raised to ln. Right, and 2 raised to L is also, it's an upper bound for the coefficients in the input. Right, so in terms of n, actually it's an exponential approximation that you are looking for. So there is the demand on C bar is very relaxed, and that will save us. Okay, yeah, so we'll basically see this we'll develop this approximation algorithm. Okay, and this was first done by L cube. So Lenstra, Lovash. So this is the main content of L cube algorithm, that they give an approximation algorithm to solve the SVP problem, and then as an application, as we have seen step 4, they can factor integral polynomials in deterministic polynomial time. Okay, so this is what we will develop in the end. We will first start with a pre-processing step. So first we do a useful pre-processing. So lemma 1, the first lemma that we will show is without loss of generality, we assume that the given vectors, right, which were B1 to Bm, till now we haven't said anything about them except that they lie in this ambient space Z to the n. So we can actually assume, and it will not change anything. So we can assume without loss of generality that they are linearly independent. Okay, so we can assume them to be linearly independent even over reals, the real field. Okay, so remember that in the input B1 to Bm could have been dependent in some complicated way, right? You could have B1, B2, and then you may have 2B1 plus 3B3, right? Or you may have 2B1 plus 3B3, and then you may have 10B1 plus 100 B2, and so on. So it is not really clear whether using integral combinations of that you can get back to B1, B2. But in this lemma we will show that if there is a dependence amongst B1 to Bm, then you can actually reduce the input instance from m to m minus 1. And if again there is a linear dependence, you can reduce it to m minus 2 and so on. Okay, so you can work with a smaller instance. One important assumption here will be that these are integral. This will be important in the proof, that we start with the integral vectors.